Hello and welcome to 37th set of video on algebra complex numbers. So before we start, I would request those who are new to the channel to subscribe to the channel and press the bell icon so that you can get updates about new and upcoming videos on this channel. Currently I'm making videos on Python programming, data structures and algorithms using C and Rust programming. So if you have interest in those programming videos, you can also watch those. I already have a playlist of C programming which has 80 plus videos. So make sure that you subscribe to this channel. I regularly upload videos and you can benefit from other videos as well. So without further ado, let's get started. As always, I will repeat that when I'm stating the problem, pause the video and try to solve the problem yourself. If you cannot solve the problem yourself, only then look at the solution. So question 361 says that prove that the polynomial cos theta plus x sin theta whole to the power n minus cos n theta minus x sin n theta is divisible by x square plus 1. So we have fx is equal to cos theta plus x sin theta whole to the power n minus cos n theta minus x sin theta. But x square plus 1 we can factorize in two terms, x plus I into x minus I. Now we substitute x is equal to I, so fi becomes cos n theta plus I sin n theta minus cos n theta minus I sin n theta, which is 0. And similarly, if we substitute x is equal to minus I, even then f of minus I would be 0. And thus we have proven the required condition. Question 362 says that prove that the polynomial x to the power n sin theta minus p to the power n minus 1 x sin n theta plus p to the power n sin n minus 1 theta is divisible by x square minus 2px cos theta plus p square. So if you factorize or find the roots of x square minus 2px cos theta plus p square is equal to 0, then the roots are p into cos theta plus minus sin theta. And we assume that we let that fx is our given polynomial. Then f of p cos theta plus I sin theta is equal to p to the power n cos n theta plus I sin n theta into sin theta minus p to the power n cos theta plus I sin theta into sin n theta plus p to the power n sin n minus 1 theta. So we separate real and imaginary parts. We have cos n theta into sin theta minus cos theta sin n theta plus sin n minus 1 theta is equal to, now these two will be equal to minus sin n minus 1 theta and plus sin n minus 1 theta is equal to 0. And the imaginary term sin theta sin n theta minus sin theta sin n theta is also 0. So our fx becomes divisible by p cos theta plus I sin theta. And similarly, you can prove it for x is equal to p cos theta minus I sin theta, and thus we have our desired result. Question 364 says that find out for what values of p and q the binomial x to the power 4 plus 1 is divisible by x square plus px plus q. So we let x to the power 4 plus 1 is equal to x square plus px plus q into x square plus p prime x plus q prime. So it becomes x to the power 4 plus p prime x cube plus pp prime plus q prime x square plus pq prime plus p prime q x plus qq prime. So comparing the coefficients, we get p plus p prime, that is coefficient of x cube is 0. Similarly, coefficient of x square pp prime plus q prime is 0, and coefficient of x pq prime plus p prime q is 0, and the last term is qq prime, there is a typing mistake here, is equal to 1. Now we assume p is equal to 0, that makes p prime is equal to 0. That also makes q plus q prime 0. But we are given that qq prime is equal to 1. So q square becomes minus 1 and q becomes plus minus I. So q prime becomes minus plus I. So now we see that the factorization is of the form x square plus I into x square minus I. Okay. Now we let q is equal to q prime, then q square becomes 1, q is equal to plus minus 1. First we assume that q is equal to q prime is equal to 1, then pp prime is equal to minus 2, p plus p prime is equal to 0, p square is equal to 2, and p is equal to plus minus square root of 2, making p prime minus plus square root of 2. So the corresponding factorization of x4 would be, x4 plus 1 would be x square minus square root of 2x plus 1 into x square plus square root of 2x plus 1. Then we can assume q prime is equal to minus 1. So p plus p prime is 0. We assume that then p prime is equal to 2 and p is equal to plus minus square root of 2i and p prime is equal to minus plus square root of 2i. So the corresponding factorization will be x square plus square root of 2ix minus 1 into x square minus 2ix square root of 2ix minus 2. So these are the three possible factorizations of the given polynomial. Find the sum of the pth p in positive integers power of the roots of the equation xn to the power xn is equal to 1. Let me make it full screen. This is question 364. So we let s is equal to sigma k is equal to 1 to n minus 1 xk to the power p. Now this is equal to sigma k is equal to 1 to n minus 1 z to the power kp, where z is equal to cos 2 pi by n plus I sin 2 pi by n. Thus, sigma k is equal to 1 to n minus 1 xk to the power p is equal to 1 plus z to the power p plus z to the power 2p and so on up to z to the power n minus 1 into p. But z to the power p is equal to cos 2p pi plus I sin 2p pi by n. So clearly z to the power p is equal to 1. If and only if p is divisible by n, in which case s is equal to n. If zp not equal to 1, then s is equal to z to the power np minus 1 by z to the power p minus 1 is equal to 0, because z to the power np is equal to 1. Question 365 says that let epsilon is equal to cos 2 pi by n plus I sin 2 pi by n for all n belonging to positive set of positive integers, and let ak is equal to x plus y to the y into epsilon to the power k plus z to the power epsilon to the power z into epsilon to the power 2k and so on up to w into epsilon to the power n minus 1 into k, where k is equal to 0, 1, 2 up to n minus 1, where x, y, z and w are n arbitrary complex numbers. Prove that sigma k is equal to 0, n minus 1 modulus of ak square is equal to n into mod x square plus mod y square plus so on up to mod w square. So from the complex number identity, we have sigma k is equal to 1 to n minus 1 ak is mod ak square is equal to sigma k is equal to 1 to n minus 1 ak into ak bar. But ak into ak bar is x plus y epsilon to the power k plus z epsilon to the power 2k plus so on up to w epsilon to the power n minus 1k n minus 1 into k into x bar plus y bar epsilon to the power minus k plus z bar into epsilon to the power minus 2k and so on up to w bar epsilon to the power minus n minus 1 into k, which is equal to xx bar plus yy bar and so on up to ww bar plus x into y bar epsilon to the power minus k plus z bar epsilon to the power minus 2k plus w bar epsilon to the power minus n minus 1k plus ye to epsilon to the power k into x bar plus x bar epsilon to the power minus 2k plus so on up to w bar epsilon to the power minus n minus 1 into k and so on up to w epsilon to the power n minus 1 into k into x bar plus y bar epsilon to the power minus k and so on up to u epsilon to the power minus n minus 2 into k. Therefore, we can write sigma k is equal to n minus 1 mod ak square is equal to n mod x square plus mod y square up to mod w square plus x into sigma k is equal to 1 to power n minus 1 y bar sigma minus k. Basically, modulus of all these terms is written here in the form of sum. Okay, but we know that k is equal to 1, sigma k is equal to 1 to power n minus 1, not power, sigma is equal to k is equal to 1 to n minus 1, sig epsilon lk is equal to 0 if L is not divisible by n from our previous problem. Therefore, all the sums in the right vanishes and we get sigma k is equal to 0 to this should be k is equal to 1. K is equal to 1 to n minus 1 mod ak square is equal to n into mod x square plus mod y square up to mod w square. Question 366 says that prove the identity x to the power 2n minus 1 is equal to x square minus 1 product of k, product from k is equal to 1 to n minus 1 into, not into, x square minus 2x cos k pi by n plus 1. So we consider 2nth root of unity xs is equal to cos 2s pi by n plus I sin 2s pi by n, where s is equal to 1 to n. Therefore, x to the power 2n minus 1 is equal to s is equal to product s is equal to 1, product from s is equal to 1 to 2n x minus xs. So we can write this as s is equal to product s is from s is equal to 1 to n minus 1 x minus xs, product from s is equal to n plus 1 to 2n minus 1 x minus xs into x square minus 1. Because xn is equal to minus 1, x 2n is equal to 1. But x 2n minus s is equal to xs bar. And therefore we can write that x to the power 2n minus 1 is equal to x square minus 1 product from s is equal to 1 to n minus 1 x minus xs into x minus mod xs bar, which is equal to x square minus 1 product from s is equal to 1 to n minus 1 x square minus 2x cos s pi by n plus 1. Question 367 says that prove the identity x to the power 2n plus 1 minus 1 is equal to x minus 1 product k is equal to 1 to n x square minus 2x cos 2k pi by 2n plus 1 plus 1. So we consider 2n plus 1th root of unity here, xs is equal to cos 2 into 2s plus 1 pi by 2n plus 1 plus I sin 2s plus 1 pi by 2n plus 1. So one of these should be wrong. I think there should be a 2 here. S is equal to 1 to n. So I think this 2, let me compare it with the previous one, 2s pi by n. So it becomes 2 pi. Okay. So there should be a 2 here. Now x to the power 2n minus 1 is equal to product from s is equal to 1 to 2 to the power n plus 1 x minus xs. However, x 2n plus 1 is equal to 1. Therefore, we can write x to the power 2n plus 1 minus 1 is equal to x minus 1 into product from s is equal to 1 to 2n x minus xs. But x 2n minus s is equal to x bar. So we can write x to the power 2n plus 1 minus 1 is equal to x minus 1 product from x is equal to s is equal to 1, there should be s is equal to 1 to n x minus xs into x minus xs bar. Now we substitute xs here. So it becomes x plus 1 product from k is equal to 1 to n x square minus 2x cos 2k pi by 2n plus 1 plus 1. Question 368 says that prove the identity x to the power 2n plus 1 is equal to x plus 1 into product from k is equal to 1 to n x square plus 2x cos 2k pi by 2n plus 1 plus 1. So this is similar to previous problems, and you can look at the solution, and if you can't understand it, then let me know in the comments. This is also similar to the previous problem, so you can solve it yourself. Question 370 says that if n is even, then prove that the identity sin pi by 2n into sin 2 pi by 2n and so on up to sin n minus 1 pi by 2n is equal to the square root of n by 2 to the power n minus 1. So we have proven that x to the power 2n minus 1 is equal to x square minus 1 product from k is equal to 1 to n minus 1 x square minus 2x cos k pi plus k pi by n plus 1. So we can say that x to the power 2n minus 2 plus x to the power 2n minus 4 plus and so on up to x square plus 1, we can write that is equal to the same value on right hand side. Just that we divided x to the power 2n minus 1 with x square minus 1. Now we put x is equal to 1. So left hand side will become n, and n will be equal to this sum. Okay. Alright. So if you put x is equal to 1, this will become 1 and this will become 1. So this will become 1 plus 1, 2. Now 2 minus 2 cos k pi by n will be 4 sin square k pi by 2n. That will be equal to 2 to the power 2 into n minus 1 sin square pi by 2n sin square 2 pi by n up to sin square n minus 1 pi by 2n. Now once we have this, we can say that the left hand side is equal to square root of n by 2 to the power n minus 1. With this, we come to the end of 37th set of problems on complex numbers. There will be one more set, and at the end of algebra, we will solve more difficult problems on complex numbers. I have left certain hard problems for the end. So we will end complex numbers in the next video. I hope that you are finding these videos useful and informative. Please share the videos on social media with your friends as much as you can. Like the video and make use of the comment box to speak your mind, to suggest uh, corrections or improvements. I know there are typing mistakes, lots of typing mistakes when I make them. So please forgive me for that. And I'm very grateful for you to for watching the videos. Thanks a lot. I wish you success in your endeavors. Thank you.